we were doing MNIST example with blanks. This class we're doing MNIST example with second half blank because we did the first half last time. And that is now in the course GitHub. Let me run all. I'm sure it'll crash at some point because at some point it's blank. But let me do a quick little, super quick recap of what we actually did last class and last class. And I really do think of it the same way I think about Lego. I do a lot of Lego with my son these days. Every morning he wants to do Lego. But that's really like we have these like building blocks of neurons. And to start with, we said the input you can think of x1, x2, all the way up to x728. So that was a picture, and it was 28 by 28 pixels, which is 728. 28 squared is 728. And so x1 to x728 are how bright is each pixel. And that is the input over here. And you can think of these as like little blobs, these neurons, and you can connect them up in all sorts of ways, however you want, right? So it's just like Lego pieces. And the first thing we did is we said, let's make one output layer over here, and we'll connect it up with weights. So we did this. And so we said a weight here, so we had W1, W2, all the way up to W728. And then we also had a vector of biases that we were just adding on. So I don't know how to do this. Let's do a plus B. And we had the formula that the output is x1 times W1 plus x2 times W2 plus all the way up to x728 times W728 plus B, right? And that was the formula that we used. And by doing this and connecting this, we called this thing the output. So we just said this is the output. Let's write output, I guess, in blue again, or let's do black. Okay. This became the output. Then we had this machine that we kind of made from this Lego of the input on one side, the output on the other side, and then we measured how well we were doing by the mean squared loss. So we took the output, we fed the output into the mean squared loss. So the mean squared error was equal to the sum of the output minus the true value squared, and average over all the examples we had. Okay, so we summed over all the examples, we divided by the number of examples to get the mean, and that was the mean squared error. And by doing so, we have an objective function, and then we minimized it with gradient descent. And the magical thing was if you can just define all these things in your programming language using that JAX package, then you can automatically do the gradient by just calling the function jax.grad. And that automatically does the gradient for you. And then you can do gradient descent on the mean squared error and minimize the mean squared error. And this is really just linear regression. Everything I've written on the board is classical linear regression. This bottom formula over here is a linear function, right? And we implemented it using JAX dot. It was a dot product of, I believe, W and X plus B. That was the function we called. That's purely linear, that's linear regression. And this mean squared error function we calculated, and we used jax.grad to do gradient descent. That was purely linear regression. And then we said, okay, well that's a little bit silly because linear regression, it can be anything between minus and infinity, but we were trying to classify digits that were 0 to 9. So then we started adding more things to it, making it more complicated. And so one thing we did is we said, instead of taking the number and making that the output right away, let's add in another layer. And this is where it starts to feel like Lego, you can just add things in. And we added in a sigmoid function. And a sigmoid function converts things that are between minus infinity to things that are between 0 and 1. So by adding in this sigmoid layer, which is like a little add-on, it converts our output, which is minus infinity to 0, 1. And that's the function e to the x divided by 1 plus e to the x. So it goes in and it comes out like that. Okay, and that's between 0 and 1. We wanted something between 0 and 9 because we had the digits. So then we put on the times 9 function. The times 9 function, x goes to 9x, that function. And we called that the output. That was called the output. And this is a non-linear regression. Why is it non-linear? Well, the first little bit is linear regression, and then we fed it through these non-linear layers over here, and so it's a non-linear regression. And then we did the mean squared error and so on. And we saw that it actually worked not too bad. So I believe we were looking at things like what? oh no, it yelled at me. Oh, I knew it would yell at me. Okay, so let's see. Did it yell at me at the right spot? So load the data set, train test split, create our functions, linear regression, training loop, training for 2 epochs. This was linear regression, right? We had things like -3 for our labels. And then we said, let's do some nonlinear regression. That's what I just said. And nonlinear regression, we trained it for 4 epochs. And we got labels like this. So it thinks this is a 2. This one it thinks is a 3.95, which is great because it's actually a 4. This one it thinks it's 1.95, which is a 1. And this 9, it thinks it's a 7.7. So it's getting pretty close. It's getting better. With this nonlinear regression, at least it's outputting numbers that are in the right range. And the numbers happen to be quite close. Okay. But then at the end of class, we said, okay, this whole thing is actually quite silly because this whole mean squared error business is not the right thing to do, right? We are doing classification. We want to know if it's 0 to 9, but not 0, 0.5, 1, like the number line 0 to 9. We want the classes, is it 0 or is it class 1 or is it class 2 and so on. So we said, let's replace this whole thing, we'll cross this out, not the mean squared error. We should be using accuracy. We should say, did you get it right? So mean squared error is not the right thing. This is a regression. This is regression. And we are actually doing classification. So we want to modify what we are doing and make it regression, or make it not regression and make it into classification. And we said that the way to do that is to add on some more layers. So drawing it one more time, we have the inputs over here, x1, x2, up to x728. And we said instead of having just one output, like we had before, so for regression you want to have just one output, some number you can measure. In classification, it's quite common to have 10 outputs, which is the class 0. Let's put it all the way on the other side over here. We'll have the class 0 probability, the class 1 probability, and all the way up to the class 9 probability. So in regression, we only had one single output, but now we have 10 outputs, one for each class. How likely are you to be in that class? And so we have to say, how are we going to connect this to this? And the first thing we said is we should have, just like before, we should have 10 layers over here. And they're exactly 10 copies of what we did before. They're just connected up like we had before by doing these sums with weights and biases. And so this is a linear layer, I'll say. And it's just 10 copies of what we had before. This is a linear layer. Okay. And so the function is, again, JAX dot dot of w comma x plus b. So same formula, but now b is a vector of size 10, vector of size 10 comma, and w is a matrix of size 10 comma 728. So w is a big vector, which is all the different weights you can have here. I guess I did not draw the last connection. Okay, so we had this, and then the question we left off on is how do you bridge this gap? So how do you go from these numbers, which are all between -infinity to infinity, and how do you convert those into probabilities, which are between 0 and 1, and there's 10 of them, and they should add up to 1. That is what we left off on. And it's a little bit like what we did over here, where we applied the sigmoid function. It's something very sigmoidy, but what is it exactly? And we did this earlier in the course, so it is a little bit of a review. These things are called the logits, or the logits, depending on who you ask. And the question is, how do you convert the logits to probabilities? How do you do that? Okay, so that is where we left off last class, and that is what the first mathematized question is. Are there any questions or comments about where we are or what we're trying to do? Okay, so let's do the first question. The first question is a very concrete example of this, which is, okay, in real life we have 10 classes. Let's pretend we only had 3 classes, just to keep things simple. So pretend you have 3 classes, class 1, class 2, class 3, and pretend the logits are 1.5, -2, and 3. So on over here, the 3 things you see are 1.5, -2, and 3. Let me make these a little bigger. Let's make this a little bigger. Okay. So pretend you see 1.5, -2, and 3. And the question is, you have 1.5, -2, and 3, and when you convert them, you're going to have 3 probabilities coming out on the other side. What are the probabilities that are associated with this -2? So how do you convert this vector 1.5, -2 to 3 into 3 numbers that add up to 1? Okay, and I gave you a few different options of different ways to do it. And I said, please pick your favorite, pick the best one. And 5 people have answered. So let me give another minute. You can stare at the formula and think. Feel free to talk to your neighbors as well. Which of these numbers should be the probability? Okay, let's take a look at what you said. What do people vote for? All right. One vote in this one, e to the negative 2 over 1 plus e to the negative 2. That is exactly the sigmoid function, right? And that is exactly what we did before. If you only have one number and you want to convert it into a probability, you can just apply the sigmoid. So if you only have 2 classes and you just have one number and you want to know how likely or unlikely it is, that's exactly applying the sigmoid function. That's converting negative infinity, infinity to 0, 1. But unfortunately, in this case, we don't just have one number. We have 3 numbers. And so that's not the right answer. Same thing with e to the minus 2. Nobody chose that. There's no way to make this one work either. So the 2 options are this, combining 1.5, negative 2, and 3. One of them has a 1, and one of them has no 1. And I think the way you can think about it is we have 3 numbers coming in and 3 numbers coming out, and these should sum to 1. Right? And because they sum to 1, if you choose this formula, presumably you would also pick e to the 1.5 and e to the 3 on the top for the other 2 classes. And then if you added up all 3 probabilities, the denominator and the numerator would be exactly the same, and it would add up to 1. So the thing that you guys chose, the most common answer, is the correct answer. So well done to people who chose that. There is no 1 plus anymore. And the 1 plus is really coming from a trick of having 1 input and only having 1 probability as the output. And there's this sort of a implicit other 1, which is the opposite happening, right? Which would be, in the sigmoid case, you do 1 over 1 plus e to the minus 2 would be the other class. So in this case, we have, this is the right answer, and that is the function we're going to use. This function has a name. It's called the softmax function. So we're going to, this big question mark, the answer is the softmax function, and that is exactly what you guys did. And the answer is that the probability is equal to the logit divided by this weird sum, so e to the logit rather, e to the logit divided by e to the sum of all the logits. The sum, I'll write it like this, e to the logit I. I going from 1 to the number of classes, and let's say this is the probability j. So every probability is proportional to e to the logit. You take the exponential of all the logits, and then you divide by the sum of all that to make sure it sums up to 1. And that's exactly the example we just did. So for example, the class 2 is e to the negative 2 divided by the sum of these exponentials. Okay, so that's the softmax function. And it was the same thing. We did this. We talked about logistic regression. We briefly mentioned this when we said if you have multiple categories, this is how you do it. It's exactly the same thing. Any questions or comments about this one? Let's see how to put it into our code. So now we're going to put this into our code. Where's the one that we're running? Okay, so load the data set, linear regression, training loop. We did all this. Okay, nonlinear regression, and then we're finally at where we are, logistic regression. This is what we're doing. Okay, and we had this formula. We did the logits, which was jnp dot wx plus b. And then we're going to calculate the log of the probabilities. So I just gave you the formula for the probabilities. And the formula for the probabilities is precisely the exponential of the logits divided by something like the sum of the exponential of the logits. That is the formula for the probability. this function is asking us to please compute the log probability. So we're going to take the log of this formula. And when you take the log of this formula, something nice happens. Let's do it on pen and paper. So we have the probability is e to the logit divided by the sum of e to the logit. So what happens if you take the log of the probability? Well, the log of a ratio is the difference. So we can do the log of e to the logit minus the log sum e. So that division becomes minus, and something nice happens here. You have a log and an exponential, it exactly cancels out. So the log probabilities are literally just the logits minus this special number, which is this thing. So the log probabilities are essentially the logits, and you just subtract this constant from them to make sure that the probabilities add up to 1. So very simple thing to do. So the answer here is going to be the logits. It's just the logits, and then it's minus this special number. And to get that number, I'm going to do jnp.log of jnp.sum of jnp.exp of the logits. Okay. All right, and I think that that will be perfectly correct. This function, so this is the probability as a comment. Probability formula. Okay, that's not what we want. Probability formula. And then we take the log. Okay, so we got the logits by doing the inner product, and then we went from logits to log probabilities by doing this thing. And let me just double check in my little cheat sheet that that is actually correct. Yeah, okay, that's perfect. Question over here?
Yeah, so logits is an array, right?
Logits is an array, that's right.
Yeah. And you're taking the sum of the entire array.
That's right. That's right.
Okay.
That's right.
And
Yeah.
log p is giving an array of all the classes. I mean, the log probabilities of all the classes.
That's right. So log p will be, what is the log probability of class 0, class 1, class 2? It'll be an array. And actually we can check by running it, that's the next thing, run it on training image 0 to make sure it's all making sense. So let's run it. Yeah, so here it is running on one example. You see it's an array of a whole bunch of numbers. On one single example, it should be 10 numbers, and a lot of them are very negative. If the log probabilities are very negative, that means that the probability is very close to 0. And then one single entry is close to 0. If the log probability is close to 0, that probability is close to 100%. So this vector of size 10 that's highlighted is saying, I really think it's really close to 100% that it's a 3. And all the other ones are close to 0. Okay. All right, any other questions or comments about this thing? So, and here it is, we batched it, right? This is something we did last time, is once you've written the function one time, you use the vmap function to make a batched version that can input lots of images at once and not just one image at a time. All right, questions or comments?
Are we taking the maximum of log p? Because we get the probabilities of, how do I say this? So
yeah,
for individual class, we are getting the probabilities.
That's right. Yeah.
So we need the maximum or the value, the class that
yes.
is classified.
So right now we have a machine that inputs the image and tells you the probability it thinks each class is.
Yeah.
If you wanted to make an actual classifier, you would have to say take the maximum or something, right? So I think it's a class 0, right? And we will do that in a minute, but that would be if we just want to know the class. When we want to train it, when we want to go from random weights to improving it, then we are going to look at the probabilities and try to improve the probabilities a bit. So it's important that we stick with probabilities now because the probabilities contain information that we can use to improve the model. So we can say like, hey, your class 3 probability is way too high. This is a 4, and you think that it's likely to be a 3. Like let's say, in this example, the first image. Actually, what is the first image? We should have a picture of the first image. The first image is in fact a 0. This is the first image, right? So the first image is a 0, and for whatever reason, the weights right now are set up so that it thinks it's a 3. So it thinks it's a 3, and it thinks it's quite unlikely that it's a 0. And so by taking these probabilities, we're going to basically tell the computer, okay, first of all, you think it's a 3 and it's actually a 0. That estimate for the probability is way too high. Please adjust the weights to lower that probability. And then we're going to tell it, By the way, the weight you put, the probability you put e to the negative 24 over here is way too low for class 0. So please up the weights so that probability goes up. That's what gradient descent does. So it's important we have the probabilities, because if we only had the final class of, I'm guessing it's a 3, we wouldn't know how to improve this number. So it's important you stick with the probabilities until the very last second. This is a really good philosophy of how this thing works, and it is similar to logistic regression. So great question. Any other questions or comments? Okay, I'm going to do one small thing that seems a little bit complicated, and it is not a mathematical thing. It is purely a computer thing. And there is this array here, logits max 0. And logits max 0, what it does is it takes the logits and it subtracts the largest one. So in the example we had, we said 1.5, negative 2, 3. If you apply the logits directly, you would get e to the 1.5 divided by e to the 1.5 plus e to the negative 2 plus e to the 3, e to the negative 2 divided by e to the 1.5 plus e to the negative 2 plus e to the 3, e to the 3 divided by e to the 1.5 plus e to the negative 2 plus e to the 3. And I'm going to insert this weird step of please first subtract the maximum. So the maximum is 3 here. So I'm going to subtract 3 from all of these things. So 1.5 becomes negative 1.5. Negative 2 becomes negative 5. And 3 becomes 0. So this is what I'm doing. I'm subtract the max. And when you subtract the max, the maximum number on the list will be 0. So everything else will be a negative number, and this will be 0. And now if you apply the logistic function, the softmax function, you get not e to the 1.5, but e to the negative 1.5 divided by e to the negative 1.5 plus e to the minus 5 plus e to the 0. And if you stare at these two numbers, you might notice this number and this number are related in a very interesting way. What is the relationship between this number and that number? Does anybody know? I'll let you think for a sec. Which one is bigger? Tell you what, let me write down this last one on the bottom over here. It's going to have the same pattern, but this one's going to be e to the 0 divided by e to the negative 1.5 plus e to the negative 5 plus e to the 0. Maybe that will help you see how to convert from one to the other. And again, same question. What's bigger, this one or that one? Which one? The one on the right?
I mean, the denominator at least, yeah.
It's true. Okay, I 100% agree with you. The denominator on this one is bigger, right? And it's actually bigger by a constant factor than the denominator on the other one, right? To get from one to the other, what do you have to do? You multiply by e to the 3. Yeah. And if you multiply by e to the 3, then the negative 1.5 becomes 1.5, negative 5 becomes negative 2, and 0 becomes 3. It's exactly going from there to there. The numerator is also bigger. How much bigger is the numerator? It's also by e to the 3. So to get from one to the other, what did you do? You multiplied the top by e to the 3. You multiplied the bottom by e to the 3. So what did we do overall to the fraction? Nothing. Nothing. They're equal. These two numbers are exactly equal. And this is why I said this is purely a computer issue. Mathematically, subtracting the maximum number and then applying this softmax function doesn't do anything. You get exactly the same probabilities coming out, either way you do it. So subtracting a constant is kind of like saying, well, these are the relative likelihoods of all the things. If you add or subtract a constant to all of them, then you're upweighting and downweighting all of them equally, and so it kind of comes out in the wash. In the numerator and the denominator, it gets canceled out. So we haven't done anything mathematically, and nevertheless, I want to do this in my program. So instead of using the logits, I'm going to use the logits max 0. So I'm going to use the logits max 0 everywhere. And this will mathematically give me the exact same thing, but there is an important reason to do it in the computer. And I will tell you what it is, but let me give you a chance to guess first. why would you want to, in your computer, why is this one, so this is the max 0 version. This is the max 0 version. So imagine you're a computer and you want to calculate this number. Why is the one on the left, this max 0 version, easier to calculate than the one on the right? Why is this one better than that one? And maybe I'll give a hint. If it's 3, it's not a big deal. But let's pretend the 3 was 3,000. E to the 3,000. Let's add some zeros to that. Then it would become an issue. Does anyone know why the computer would prefer the one on the left than the one on the right? Yeah.
Convergence rate?
Convergence, what do you mean by convergence rate?
Like when we'll be learning, like we'll be shifting from test RMSE to what we want to achieve.
Right.
Into converging faster?
Well, they're, in terms of what they do, if it's computed correctly, it will do the exact same thing because they're equal, right? So they're mathematically equal. So the solution is not going to be that there's some difference in the convergence rate or there's some actual difference. The answer is going to be the computer, the way the computer works, because it has finite memory and finite many bits, it's going to make an error when you compute one of them.
Number will be too big.
Yeah, the number will be too big. That's right. So this number, e to the 3,000, is so big that if you put in a number that's too big and you do the exponential of it in the computer will not try to calculate it. It will just say infinity or not a number. And so when you apply the exponential function, you have to be careful that the things you are feeding in are not too big or the computer will explode and get mad at you. So you can do this, it's mathematically correct, but it will throw errors sometimes. On the version on the left, the highest number is 0, right? That's why it's the max 0. And because it's the max 0, it will never ever output something higher than 1. All of these individual things are at most 1. There is the opposite problem of what about e to the negative 3,000, right? Like if you're subtracting 3,000 from all the components, you'll have things like e to the negative 3,000. And the computer explodes when you feed an e to the 3,000. It says, infinity, not a number, this is terrible. What happens when you do an exponential of negative 3,000? Again, the computer doesn't do it exactly, it just says, oh, well, that's 0, right? So the computer has this asymmetry in its types of errors. If you feed in a big number, it says infinity, and that's a real issue. But if you feed in a too small number, it just says, oh, that's exactly 0. And then that's fine. You know, we can have zeros in here. 0 plus something is fine. Infinity plus something is not fine. So by doing this max 0 version, we avoid this kind of error, and it makes things run more smoothly. So purely for performance purposes, I'm doing the log p with the logits max 0. Okay. So that's the probability function, the log probabilities. And that's working. And I V-mapped it, so now it works on a full batch. Let's run this again and make sure things are working. Okay. It died. I think it died. Oh, okay. You know what? I'm just going to run everything, I guess. Runtime. Run before. Okay. While this is running, let's work on the next thing, which is before, when we were working last class, we used the mean squared error. And I said the mean squared error is for regression. We're going to replace that. Does anybody remember what you use instead of the mean squared error? What kind of loss function do you use? So the loss function equals what? What is the loss function that you use for classification when you have probabilities? The cross entropy loss. So very good. The cross entropy loss. Cross entropy. And we had a class many weeks ago, loss, where we talked about where does the cross entropy loss come from? It comes from the Bernoulli probabilities. And to remind you how cross entropy loss works, we have another problem. So you're working on a classification algorithm. For a particular example, your algorithm thinks the probabilities are 0.2, 0.3, and 0.5. So we've already created the probabilities. If the true label is at class 2, then the cross entropy loss is which of these? So you might have to open your notes and see how does cross entropy loss work. If you remember very well, then maybe you remember. But one of these is the cross entropy loss. So try to remember how cross entropy loss works and what the formula is. I'll give you 2 minutes. Feel free to talk to your neighbors. And then we will implement it in the code. Okay, let me put this back. All right, let's see what you guys think for cross-entropy loss. Which of these is the formula for the cross-entropy loss? In this case, how do you go from probabilities to cross-entropy loss? Let's reveal counts. Oh, some kind of bug. Okay, let's close this and try to reopen it. View responses. Let's try again. Okay, here we go. Better. Okay, pretty even split. Nobody fell for the trick over here. So the trick over here, this first one, is that would be a mean squared error way of doing it, right? You have a vector that you actually want, which is you actually wanted it to be a 1 in the second component. Nobody fell for that. So everybody knows it involves a log somehow. It involves the log probabilities. This is, by the way, this is the reason I made the function output the log probabilities instead of the probabilities. Because we actually just need the log of the probabilities. If you know the log of the probabilities, you can compute the cross-entropy loss. But which one is it? As usual, we have the perfect split. Out of 9 people, we have 4 to 5. For, is it the log probability of the class, or is it the log probability of the other ones? And I think you could figure out which it is. Imagine that it was getting it perfectly right, or like really close to right. Like, let's say it put 99% probability of class 2, then we should have a very low loss. So think about which of these numbers is low if you have 99% in class 2. And which one? One of these will be low, one of them will be high. I'll let you think about it. So I'll give you 2 minutes to try to guess, or you can, again, talk to your neighbors, look at notes. Which of these is the correct thing? Okay, so let's revote, repeat exercise, and do it again. Okay, so here you go. Open one more time. Which of those two is it? Okay, 1 minute. Put in your final guess. Okay, 3 seconds for the ninth person to put their vote in. Okay, maybe they fall asleep. Okay, let's take a look. Oh, there they are. Okay, 9 out of 9 dentists agree. The answer, well, 6 out of 9 dentists agree. The answer is negative log of 0.3. So some people moved into that camp, and that is the correct answer. So if you got this one, congratulations. You can see if 0.3 was replaced with 0.99, then you would have negative of the log of a number really close to 1, and the log of 1 is 0. So you would have a loss that is very close to 0. The loss is like how much you get hit over the head with a newspaper when you said your guess, right? So it's like if you say 30%, I think it's class 2 30% of the time, and then it's like 30%, you idiot. No, big loss, right? 99%, you're like, okay, small loss. All right, 99 is pretty good. On the other hand, this function, if you replace the middle one with 99%, then 0.2 and 0.5 would get replaced with like 1%. So it would be the log of numbers close to 0. And the log of numbers close to 0 are huge, because the log of 0 is minus infinity. So these would be a huge loss for saying 99% chance of it being class 2, which is not what we want. So that's one way to do it. But the formula in general is for the cross entropy loss. Cross entropy loss, it is the log of p hat of true label. And if you have multiple things, so for a true label, and we saw that in class, the cross entropy loss for a probability for p is the sum of pi times the log of p hat I. So if one of the p's is 100% and the others are 0, then you get exactly the other one. And the way we're going to implement this in our code is we're going to use this kind of formula. So we're going to convert our true label, instead of thinking of it as an index, we're going to convert it to a vector, a one-hot vector. So we're going to take our true label. So in the example, the true label was equal to 2. We're going to convert this into a one-hot vector, 0, 1, 0. And then we're going to do 0, 1, 0 times 0.2, 0.3, 0.5. And then that will give us this sum that we want, or the log of the true thing. Okay, I forgot the log function. Let me apply the log function first. So log of this, log of this, log of this. And if you do this dot product, it will add these up for you. So we can take the cross entropy loss as really some kind of dot product. So let's do that in the code and show you what that looks like. So what I did is we're converting it to a vector, a one-hot vector. That's the classification, a one-hot vector. And there's a function for this that is a nice function that exists in JAX. It's called jax.nn.1hot. And that will convert a vector of numbers into a one-hot vector of size 10. And so the number we're doing is the target. The target is the true label. And if you just run it like this, it doesn't know how many zeros to add. So I'm going to add 10 because there are 10 classes. So 10 tells it the number of classes. So that's going to make a vector of size 10. And then what is the cross entropy loss? Well, I take the log probabilities. So let me call this, let's give this a better name, the prediction log probabilities. And to combine the prediction log probabilities with the target, I will do the prediction preds log probabilities times the target as vector, and then I will take the mean. JNP.mean. I believe you could also do this as a dot product, but let's do it like this. Oh, not the mean, the sum. We want the sum. Of course we want the sum. Okay, the sum. And there's one thing I'm missing. This is a very easy to miss thing when you're dealing with logs and losses. Does anyone know what I'm missing? I'm one character away from getting it right.
Negative.
Negative, yes. Once again, if you forget the negative, then nothing will work, because instead of doing gradient descent, you'll do gradient ascent. You'll be making it as bad as possible, right? Which is not what you want. So you gotta make sure you get the negative signs exactly right. Okay, so let's run this now, and now everything should be working. So here is our log probabilities for one single example. Here's the batch log probabilities on all the examples, and here is the cross entry loss that it got, which is quite huge, 30,000 or something like that. Okay, the cross entry loss. Okay, and now we are ready to run it. And this is the amazing thing about this stuff, is we don't even have to rewrite that training function. We use the exact same training function we had before. It automatically computes the gradient of whatever you have, right? So you just tell it the loss function you want, you tell it what you do, and then it just goes and it trains it. So I'm going to rerun the code over here. I added this function called the top one accuracy, which is saying how often is the thing that you had the highest. Oh, I never filled it in. The predicted class, this is exactly what we talked about earlier, is the maximum jnp.argmax of batched log gr log p params images. Okay, so there's this. So far, everything will work. We have the cross entropy loss, and everything is working. So here is the train loss, here is the test loss, and it's adding everything up. Okay. And then let's see how it's doing. So it thinks this one is a 0. It thinks this one is a 4. It thinks this one is a 1. And it thinks this one is a 9. It's doing very well. So one way you can see how it's doing in a little bit more human-readable way, instead of looking at the loss, you can look, like I said, at the accuracy. And how do you get the accuracy? Well, you just say, is the thing with the highest probability, is that the right answer? And that is what this is doing, so the argmax takes the highest probability. I'm going to do one other thing here. I am going to switch this from the sum to the mean, and the reason is I think this is taking a batch. So is this eating a batch of images? Because if it's eating a batch of images, we want to average over the number of images. And the cross-entropy loss, look, it's taking all the images. So by doing mean, it's averaging over all images, so it's giving you the average cross-entropy loss instead of the total. So that'll be a little bit nicer to look at. And now my argmax is working. The top one accuracy is the thing with the highest value, the correct answer. And now as you run it, it will also report the accuracy as you go. And we had that as in our training loop, we had a thing that was like inputting the accuracy function. So you can check this as you go. Okay, so after one round of training, the average cross-entropy loss is 2.5 or 2.8 on the training test set respectively. And more human readable is the average accuracy is like 85%. So that's pretty good. We're getting 85% of the time, the true answer is what we think is the highest probability. And then look, it goes up to 88% of the time. And this again is plotting what is the highest possible label. We think it's a 0, we think it's a 4, we think it's a 1, and we think it's a 9. So it's already doing really well, 88%. This is just logistic regression. And it's all implemented in this like really flexible Lego way. All right, I think all of the main things are here. All of the hard parts we've done. The hard parts are this whole thing with the softmax, and then this whole thing with the cross-entropy loss. If you understand those two things, then it becomes completely trivial to make it a really complicated neural network that can do all sorts of amazing things. So we've done the hard parts, and we're gonna, in a second, we're gonna just like amp it up and just like take our bin of Lego and dump it on and just like make it really complicated and fun. This is a great time to stop and ask for if there's any questions about either of these two important steps, the softmax or the cross-entropy part. Yeah?
Can you just scroll down?
Yes?
Yeah, move to the last slide. Yeah, can you just explain this last 1010? Why did you do that?
Okay, yeah, so, yeah, this is great. So what I want to do is I really would like to have the log of 0.3. So I would like to convert the true label of 2 into the log of 0.3, right? That is what you guys did in the mathematizer example.
And now, when you go to the code, basically you're creating, when you do one-hot encoding, basically you're creating a matrix 10 cross 10, right? Which gives the class for a vector for individual class.
Right. So target is actually a list of all the training labels. So it's 10,000 long.
Yeah.
So it's 10,000 numbers. It's like 2, 7, 8, like it's all the numbers. And then when I make target as vector, it converts that list. It converts each number into a vector of size 10. So the list of size 10,000 becomes a 10,000 by 10 matrix.
Yeah.
And then that 10,000 by 10 matrix, when you do the predictions, it's all set up so that it's averaging over the size 10,000. So it's telling you what is the average per example. And so another way to do this, I could have written it for one vector and then done a batch version. I could have done JAX dot vmap to make a batch version, but this is written as the batch version already. Yeah. So maybe that was that's why it has to be mean here, not sum. Yeah. Great question. Yeah, and again, this is like this whole idea of keeping track of the dimensions is like really important when you do these neural network things. There's a lot of the coding comes down to this kind of thing. Okay. Any other questions or comments about what we have so far? So far we've done logistic regression, which is something we did earlier in the course. So like, what's the point? Why did we spend 2 classes just to do logistic regression? And the answer is, now that we have this, we can make it more complicated. And so one thing we can do is we can add more layers. So instead of just having one layer like this, let's do a bunch of layers, right? So we take our Lego, and the nice thing is, instead of having one layer, this is like multi-layer, version. And all we got to do is just have x1 all the way up to x728. And we have this layer. We just add more layers. We just add another layer and another layer. And as long as the last layer is size 10, these ones can be any size, any size, any size. So you have some matrix of weights, W1, the first layer weights, the second layer weights, the third layer weights. Then at the end, you get a vector of size 10, and then you can apply softmax to this. So softmax, just like we did before, and that gives the log probabilities. And so the point is, everything we've done, we've explained how to do this. These layers, the first three, are just repeats of the first layer. You just do matrix multiplication again and again, you can have more than one W. And everything is set up in our code that to do this is very simple. So let's do it. So this is a multi-layer perceptron with cross-entropy loss. You tell it what the size of the layer sizes you want. And we want to start with 728. Not 728, 784. I've been saying 728 the whole time, which is wrong. Okay, 784. And so the layer sizes we want are 784, something, something, and 10, for example. So as long as we end with the size 10. And we can put in anything we want. For fun, I put in, what number did I put in? I did 2. I did 1 of 784. So 784 to 784, and then 784 to 10. And the nice thing is everything is written so that it will still work. So the parameters, this function will still work. It'll just take into account these layer sizes, and it will automatically create those matrices, W0, W1, to work. And then I will do the function. So this is the MLP, multi-layer perceptron. This is the function we're defining. And it's going to input the image, and it's going to input the parameters, and it's going to calculate the log probabilities. And the way it works is the same as before. The first layer is exactly what we had before, JNP dot of WX plus B, right? I take the W and the B from the first layer. I do JNP dot WX plus B, exactly what we had before. And then I loop through all the layers, and I just keep doing it. So X is, again, just JNP dot of W and X. So yeah, W and B are selected in the loop, and then I just keep doing it. JNP dot of WX plus B. So I just take the X from before, I multiply it by W, I add B, and then the last layer, I calculate the logits, just like we did before. JNP dot of final W X plus final B. Okay, and that is the logits. This is the logits max 0. How do you convert from the logits to the log probability? That's the formula we just did. So it's the logits max 0 minus JNP.log of JNP.sum of JNP.exp of the logits max 0. So basically, essentially copying and pasting the code we had before, but now with a for loop that does it a bunch of times. So loop through all the hidden layers and do it. Okay, and hopefully it'll work. If you get your brackets right, that works. Whoop. Does this work now? Okay. Help me find the bug, guys. 3 brackets. What does it not like? Log gets max 0 is not defined. You got to put an I right here. All right. All right. And there you go. So it works exactly the same as the logistic regression function. The output is, again, a vector of size 10. And all we did is we added more layers, right? We multiplied. We did, instead of doing 1 matrix multiplication, we really did 2. So we have like X at layer 1, X at layer 2, X at layer 3. And we're doing X1 is equal to W1 times X input plus B. X2 is equal to W2 times X input plus B. And X3 is equal to W3 times X, not X input, the previous layer. All right, X1, X2 plus B. And we have 3 layers of B's as well, B1, B2, B3. So we're taking what we did before, and instead of just doing it 1 time, we do it 3 times, then everything else is the same. And let's see how well it works. So before, our accuracy was like 83% or 88%, right? We were getting 88% accuracy. Everything will work yet again. Yeah, you make the batch version, same function as before. You make the loss function, same loss function as before, cross-entropy loss. And now you run it, and let's see how well we're doing. Okay. So it takes a little bit longer now because there's more computation to be done, right? Every time you feed it an example, it has to go through multiple layers. It takes a few seconds longer. All right, let's see how we're doing. All right, so our first, after one epoch means feed in the examples one time. Our training accuracy is 85%. What was it in logistic regression? In logistic regression, it was also about 85%. Okay, so maybe after 2 epochs, it will get better. Oh, okay. Now it's like 86% accurate, which is pretty similar to what it was before. Before it was like 88% accurate. So very similar numbers in terms of accuracy as before. So I added a layer. I really did add one layer. And now I have almost the same accuracy. Yeah.
Earlier it was 83.
Yeah, it was like 83 and 88 or something. Let's go check. So 84 and 83 and 88. And now it's almost exactly the same numbers. It's 84 and 86. So very slightly worse, almost exactly the same. So what did we do? Why isn't it improving? We added layers, we added more parameters, right? More parameters, it should fit better. Maybe we have an overfitting problem, but at least the training error should go down a lot, right? When you add more layers. And so what we did is we did this thing, we added more matrices, right? And we did this matrix multiplication repeatedly, right? In specifically the example I did 2 of them, and one of them is a 784 by 784 matrix. We just multiplied it up. And if you're literally doing matrix multiplication like this, which is what we have so far, it turns out we haven't done anything. We haven't done anything. So if you stare at these 3 equations, there's actually a way you can condense this down into just one equation. You can condense 3 matrix multiplications into x3, that's the output, is something something in terms of x input, right? So I had x1, x2, x3. I did add more layers. But what layers did I add? I just did matrix multiplication every time. And instead of doing multiply by this matrix, multiply by that matrix, multiply by the third matrix, there's a simple way you can go from the input straight to the output, which is to just multiply the matrices together. So you could just do W1, W2, W3. I guess you got to do it in the opposite order. W3, W2, W1. Okay, and there's going to be some stuff with the B's. There's going to be some D added on. But essentially what I've done by adding more layers with matrix multiplication, it's still matrix multiplication. If you matrix multiply 3 times, that's matrix multiplying 1 time with a different matrix. So have I actually changed the model at all? I haven't, right? To go from the input to the output is still a linear function, and the computer is still trying to find the best way to do it. We're representing it differently in the computer. Instead of 1 matrix connecting the input to the output, now there's 3. But it's the same space of possible things, which are linear functions from the input to the output. So far, this is literally doing nothing. And it kind of shows in our results, right? We got the exact same results using 3 layers or using 1 layer with logistic regression. So far it's doing nothing different. You have to add in a special secret ingredient to really get something different. And that secret ingredient is nonlinearity. So far everything I've said is linear all day long, except for the softmax layer at the end. But the x1s, x2s, and x3s are all linear functions of the input right now. And so the way to make things exciting and to get a new space of functions is you add in a nonlinearity. And you can do that at every single layer. So I'm going to insert this new secret ingredient. Let's pick a special color here. The new secret ingredient goes after every single layer. And that secret ingredient is nonlinearity. Nonlinearity. And what I'm going to do is I'm just going to take the vector, and to every single entry, I'm going to apply a nonlinear function to it. And by doing that, I'm going to break the cycle. You won't be able to write it as a matrix multiplication anymore. It's going to be some completely new function. And so by just applying a little nonlinear function to every single entry, I can like expand the space of possible functions that I can represent. And we know that like what digit it is a very nonlinear function of the actual input image. So this is a good idea to expand the space of functions. And fortunately for us, it's really easy to do because we have this setup of like writing out what the function is in a very simple way. So all I gotta go where this thing is written, and there's even space for it, is to apply transformations. So I have x transformed and x transformed. And this is just saying, after you do wx plus b, you apply a transformation to it. And the function I'm going to apply is called the ReLU function. So and I have it written up here, the ReLU function. I'm just going to do ReLU of x, and that will transform the data. Okay? So I'm just applying ReLU of x after every time. One thing here, over here, I don't want to apply this to x. I want to apply it to the transformed x. So when you go from one layer to the next layer, you take the transformed values and use those. So the nonlinearity I'm using is the ReLU function. So this is ReLU. This is called the ReLU function. And what is the ReLU function? It's a very simple function. The ReLU function. The ReLU function is it looks like this. It's the function ReLU of x is equal to the maximum of x and 0. So it's 0 if you're a negative, and then it's x if you're positive. So it does nothing if you're a positive number, it just lets you through. And then if you're negative, it sets you to 0. Okay, so I'm going to do that. ReLU is the maximum of x and 0. That is right here. J and P dot maximum of x and 0. And now I have transformed my thing by applying this nonlinearity, and it should work quite nicely. So I've done it. Still outputting things that look the same of log probabilities. Make the batch version. Loss function is exactly the same. And now when I do it, it should get quite a bit higher accuracy. So before it was like 85%. Now it should be a little bit higher. Let's see it work. Okay. This is 784. Okay. And again, it's a little bit slower because you have to call a bunch of things. There's a lot of computation going on. It has to go through that whole graph that you had before. Uh-oh, it started the same. Okay, let's see if it actually improves. Okay, not much improvement here. Maybe I have a mistake. Let's make sure everything is running correctly. X transform. Aha! Do you guys see what I did? Do you see? I changed x to x transformed up there, x to x transformed here, and then in the final layer, I said take x and use it, right? But I don't want to take x and use it. I want to take x transformed. So otherwise, you are just doing literally what we had before. Okay, transformed. This is a good kind of bug to sort out. Okay, let's try it again. Run everything again. And let's try one more time. All right.
But I think we performed ReLU at least once, right? Like we performed ReLU once, and then you were considering it.
Right. So let's go look at the code. So the way it works is after you do a layer, you will perform the ReLU.
Yep. And
yeah.
At the end, where it
yes.
says logic is equal to, at least once we were adding ReLU, that was two parameters, right? Okay,
so in the last layer, there is no ReLU. So in the picture, where is the picture? Right, so the ReLUs only get added on these linear layers. So you apply a matrix W, and then you do a ReLU. You apply a matrix W, you do a ReLU. You apply, in the last layer, you apply the matrix W, and then you do the softmax business to get the log probabilities. So you only do the ReLUs in these like linear layers. Yeah, yeah, and that's, I mean, you could apply it at the end here, but there's sort of like, we're already doing a bunch of stuff there. Like, you don't need to do that. Okay, so let's take a look. Did it actually improve? Hopefully. Ah, here we go, look at this. 95% accuracy after just seeing the images once. We went through all 10,000 images once, and we already got to 95% accuracy. And then we did it again. Let's look at the images one more time. And we improved from 95% accuracy to 96.9% accuracy. So going up, again, a last little bit. Yeah?
Is this the impact drawn by ReLU function?
Say that again?
Is this the impact created by ReLU?
Well, like why is it doing this?
Why is it 95 right now? Like, why a certain jump?
Okay, so I think, like, why did introducing ReLU improve it from 85 to 95? So when we added the ReLU, we really extended the possible functions that could be represented by our neural network, right? So our neural network has parameters, and by changing the different parameters, it can express different functions, right? And if you have a ReLU in there, it can express all these kinds of crazy nonlinear functions that have bends in them. If you don't have the ReLU, it can only express linear functions, right? And the point is, the problem of taking an image and saying what digit it is very nonlinear. So by allowing the computer to express nonlinear functions, by adding in this ReLU, we were able to express a function that is really close to the true function. If you only have linear functions, it's not able to express it as well. So we've kind of like broken free of the shackles of linearity. Like that's really what we did. And it doesn't have to be ReLU. The same thing would happen if you did like any nonlinear function. Just chuck in any nonlinear function so that you're not stuck in linear land, right? And the point is that when you apply, the point is that linearity is preserved under applying it many times. So adding many layers on its own will not increase the space of functions because it's always a linear function. Linear applied to linear, applied to linear, it's still always linear. But if you do a linear and then you do like a little tweak to it to make it nonlinear, then you become this nonlinear function, right? And you're like way bigger, right? It's sort of like building into a third dimension. It's like linear functions, you keep going in linear directions, it's like you're a two-dimensional person, and then all of a sudden someone says, if you just do this weird thing and go up, now you have this whole other space you can explore. Like, so if I give you two-dimensional things, you can only build in 2 dimensions. But if I give you two-dimensional things and every now and then I say, by the way, here's a little ladder, you can go up if you want. Now you have access to a whole new space. And it really is like a lot bigger. So that's why the ReLU helped. And that's why we're doing so well. Did I answer your original question? I don't remember. Yeah. Okay. Yes. I think it's really weird. Like, why is it all of a sudden doing better? It's kind of crazy. And actually what we've done is I've like fast forwarded like many decades of AI research, right? So for a long time, people were stuck with this problem. And I think even as recently as like 2010, the highest that anybody ever got was like 90%. And we just beat that. We got like 95%. This is already like 2010 kind of things. So we're doing quite well. And I will say the other nice thing is you can play with the hyperparameters. You can just add more layers. Like, how do you add more layers? You just type in layer sizes, and everything is set up to automatically run. So here is one that has yet another layer, and I think this one gets even higher. So it's got 3 layers of size 784. It's applying the ReLU twice. It actually looks like the picture that I drew over here. It's got 3 layers of size 784, and then 1 layer of size 10. And you can make these any number you want. You can play with these layer sizes and see how it works. It really is kind of a guess and check to see what's the best. But when it works quite well. And again, the bigger you make it, the slower it trains, because it has to do more computation every time you do it. But after 1 epoch, our loss is what? We're up to 92% after 1. Oh, maybe I trained it for longer. Oh, okay. Okay, so I was looking, let's in the interest of time, let me show you the cheat sheet I had. So this is the same exact thing, but already done. Where did it go? So MNIST example is in the GitHub is the solutions that I've been copying from whenever I get stuck. And we have exactly the same layer sizes, 784, 784, 10, but I ran it for 10 epochs. So here it is, epoch 1, epoch 2, and so on. And you can see that by the end of 10 epochs, it is up to 98%. So the train accuracy is 98%, and the test accuracy is 97%. So only 2% of images it's getting wrong. And you can check and see how it's doing by plotting some examples. So here are some examples. These are ones where it got them, these are just some random examples. And you can see it got all of these examples correct. So 0, 4, 1, 9, 2, 1. It's got it 100%. Of these 9 examples, it's perfect, right? Which is not surprising if it's 98% accurate. I wrote some code to please show me the examples where it's not working. Please show me the examples where it's not working. And these are the digits. It's like searching through the whole list to find the examples that it's getting wrong. Here are the ones it's getting wrong. And you can see they're all kind of messed up. Like that one, it thinks it's a 0, but it's actually a 9. If I was going to look at that as a human, I might say that's an 8. So the ones it's getting wrong are ones that the human writing kind of screwed up, right? Here the computer thought it was a 1. This is actually a 2. But you can see, you can be like, okay, I can see why you thought it was a 1. Here it thought it was a 2. Apparently this is a 3. This is labeled as a 3 in the data set. I would say that's a 2, right? So we're up at the accuracy of 98%. Is at the limit of what the human accuracy is, right? Like 98% right is very, very good for this data set. A human will be about 98% right. So we're sort of like in this simple thing. We started with linear regression. We did a couple tweaks to linear regression. And by doing this nonlinearity thing and adding more layers, you can all of a sudden get this like superhuman performance on this data set. Okay, so we'll stop there. Next class, we'll see different things you can do with neural networks. So we're going to see how you can modify PCA. PCA was this embedding of a high-dimensional vector space into a low-dimensional vector space. Again, linear, right? It was a linear embedding. We can make a nonlinear embedding by using a neural network. And we'll see there's all sorts of crazy things you can do with that. So that'll be next class. And yeah, okay, we'll see you guys on Thursday. I'll be around for a few minutes. If you have questions after class, come on up and let me know. But otherwise, see you on Thursday.